Have you ever stopped to think about the invisible forces that shape our world? Physics isn't just for scientists in labs, it's at play in every aspect of our lives, from the moment we wake up to the time we go to sleep. It explains why things fall, how we hear music, and even why the sky is blue. Let's uncover some of these hidden laws of physics that govern our everyday experiences. Get ready for a mind-blowing journey into the ordinary. Ever notice how your hot coffee cools down faster on a chilly day than on a warm one? That's Newton's law of cooling in action. This law states that the rate of heat loss from an object is proportional to the temperature difference between the object and its surroundings. The bigger the temperature difference, the faster the cooling. Think about a crime scene investigation. Forensic scientists use Newton's law of cooling to estimate the time of death based on the body's temperature. They measure the body temperature and the ambient temperature. Then they apply the law to calculate how long ago the body reached its current temperature, providing crucial clues for solving the crime. Airplanes soar through the sky, seemingly defying gravity, but it's not magic, it's Bernoulli's principle. This principle states that as the speed of a fluid like air increases, its pressure decreases. Airplane wings are designed with a curved upper surface and a flatter lower surface. This shape forces the air flowing over the top to travel faster than the air flowing underneath. The faster moving air above the wing creates an area of low pressure, while the slower moving air below creates an area of high pressure. This pressure difference generates an upward force called lift, which counteracts gravity and keeps the plane aloft. It's a beautiful example of how physics enables us to achieve seemingly impossible feats. We've all heard the siren of an ambulance approaching, its pitch getting higher as it gets closer, creating a sense of urgency and alertness, and then lower as it moves away, fading into the distance. This phenomenon is known as the Doppler effect, and it's not limited to just sound waves. It applies to all types of waves, including light waves, which can be seen in the way light behaves when it passes through different mediums. The Doppler effect describes the change in frequency of a wave in relation to an observer who is moving relative to the wave source. This principle is fundamental in various fields of science and technology. When the source of the waves is moving towards the observer, the waves are compressed, resulting in a higher frequency, higher pitch for sound, bluer light for light. This is why a car engine sounds higher pitched as it approaches you. Conversely, when the source is moving away, the waves are stretched, resulting in a lower frequency, lower pitch for sound, redder light for light. This explains why the sound of a car engine drops in pitch as it drives away. Astronomers use the Doppler effect to determine the speed and direction of stars and galaxies. By observing the shift in light, they can gather crucial information about the universe. By analyzing the light from these celestial objects, they can tell whether they are moving towards us or away from us and how fast they are traveling. This helps scientists understand the expansion of the universe and the movement of galaxies. Section 5. The law of conservation of momentum, the physics of collisions. Remember playing pool? It's a perfect example to understand this concept. When you strike the cue ball, it transfers its momentum to the other balls, causing them to scatter in various directions. This transfer of momentum is a key principle in physics. This is a clear demonstration of the law of conservation of momentum, which is fundamental in understanding collisions. This fundamental law of physics states that in a closed system, the total momentum before a collision is equal to the total momentum after the collision. This means that momentum is conserved and not lost. Momentum is a measure of an object's motion and is calculated by multiplying its mass by its velocity. The greater the mass or velocity, the greater the momentum. The law of conservation of momentum explains why a heavier bowling ball will knock down more pins than a lighter one traveling at the same speed. The heavier ball has more momentum. It also explains why airbags in cars are designed to inflate rapidly upon impact. They play a crucial role in vehicle safety. By increasing the time over which the collision force is applied, airbags reduce the force experienced by the occupants, potentially saving lives. This extended time helps to lower the impact force significantly. Section 6. Friction, the force that makes motion possible. Friction is often seen as a nuisance, but it's actually essential for our everyday activities. Friction is the force that opposes motion between two surfaces in contact. Without friction, we wouldn't be able to walk, drive cars, or even hold objects in our hands. Imagine trying to walk on a perfectly smooth surface like ice. Your feet would slip and slide, making it impossible to move forward. Friction is what allows our shoes to grip the ground, our car tires to grip the road, and our hands to grip a doorknob. It's also what allows us to write with a pen or pencil. The friction between the tip of the writing instrument and the paper creates a resistance that allows the ink or graphite to be deposited onto the surface. Section 7. Surface tension, from insects walking on water to soap bubbles. Have you ever wondered how insects can walk on water? It's all thanks to surface tension. Surface tension is the cohesive force that exists between liquid molecules at the surface of a liquid. The molecules at the surface are more strongly attracted to each other than they are to the air molecules above, creating a thin, elastic-like film on the surface. This surface tension is what allows small insects like water striders to walk on water without sinking. Their weight is distributed over a larger surface area due to their long legs, preventing them from breaking through the surface tension. Surface tension is also what gives soap bubbles their spherical shape. The soap film minimizes its surface area to achieve the lowest energy state, resulting in a sphere. Section 8. Capillary action, how plants quench their thirst. Plants need water to survive, but they don't have mouths to drink. So, how do they get their water? The answer is capillary action. Capillary action is the ability of a liquid to flow in narrow spaces, even against gravity. This phenomenon is driven by the combination of cohesive forces between liquid molecules and adhesive forces between the liquid and the surrounding material. In plants, water is drawn up from the roots to the leaves through tiny tubes called xylem vessels. The adhesive forces between the water molecules and the walls of the xylem vessels are stronger than the cohesive forces between the water molecules themselves. This allows the water to climb up the xylem vessels, defying gravity and reaching the leaves where it's needed for photosynthesis. Section 9. The physics of cooking, heat transfer, and chemical reactions. Cooking is more than just following recipes. It's a delicious application of physics and chemistry. Every time you step into the kitchen, you're engaging in a scientific experiment. Heat transfer plays a crucial role in cooking. Without it, we wouldn't be able to transform raw ingredients into delicious meals. Heat can be transferred through conduction, convection, and radiation. Each method affects the cooking process differently. Conduction is the transfer of heat through direct contact, like when you cook an egg on a hot pan. The heat moves from the pan to the egg, cooking it thoroughly. Convection is the transfer of heat through the movement of fluids, like when you boil water in a pot. The hot water circulates, evenly cooking whatever is in the pot. Radiation is the transfer of heat through electromagnetic waves, like when you bake bread in an oven. The heat radiates from the oven walls to cook the bread. Chemical reactions also play a vital role in cooking. These reactions can transform the ingredients in surprising and delightful ways. Heat can trigger chemical reactions that change the texture, flavor, and aroma of food. For instance, the Maillard reaction gives seared meat its delicious crust. For example, that when you bake a cake, the heat causes the baking powder to release carbon dioxide gas, making the cake rise. This is a perfect example of a chemical reaction in action. Understanding the physics and chemistry of cooking can help you become a better cook and unleash your inner culinary scientist. With this knowledge, you can experiment and create dishes that are not only tasty, but also scientifically fascinating. Section 10. The physics of music, sound waves, and harmonics. Music is a universal language that transcends cultures and languages. But have you ever stopped to think about the physics behind the sounds that move us? Sound is a form of energy that travels as waves through a medium, such as air or water. When we hear music, our ears are detecting vibrations in the air caused by these sound waves. The pitch of a sound is determined by its frequency, which is the number of waves that pass a point in a given time. Higher frequencies correspond to higher pitches. The loudness of a sound is determined by its amplitude, which is the height of the sound waves. Larger amplitudes correspond to louder sounds. Musical instruments produce sound waves with specific frequencies and amplitudes, creating the melodies and harmonies that we enjoy. Section 11. Conclusion: appreciating the physics of everyday life. From the cooling of our coffee to the flight of airplanes, physics is all around us, shaping our everyday experiences in subtle yet profound ways. By understanding these fundamental laws of nature, we gain a deeper appreciation for the world around us and the marvels of the universe. So, the next time you sip your morning coffee, watch a plane soar overhead, or listen to your favorite song, take a moment to appreciate the elegant physics that makes it all possible.